Hello, everybody. My name is Bashir Sadiqi, and I will be presenting our paper titled as On Characterizing the Trade-off in Invariant Representation Learning, co-authored by Sepeh Dehdashtian and Dr. Vishnu Bodeti. There is an increasing impact of machine learning in our daily life, where for the input data X, the target predictor GY is trained to predict a desired target attribute Y. For example, in face recognition, GY predicts the identity of input faces. Transfer learning aims to predict a target attribute from a data domain that it has not been trained on, or it has been weakly trained on. There is an increase in loan approval decision-making by machine learning systems nowadays. Machine learning is also deployed to assist with university admission. Moreover, some courts use machine learning algorithms for recidivism prediction that aims to predict whether an offender will again commit a crime or not. However, the role of machine learning can be concerning since face recognition systems may have a bias with respect to a skin color. Machine learning algorithms may not generalize well to some data domains. Loan approval decision-making may be unfair for some races and genders. University admission may have a bias with respect to race and age. Recidivism prediction by machine learning algorithms has previously shown a bias for some ethnicities. So, where does the bias take place? Most prediction algorithms can be accomplished via training an encoder F to learn a compact representation Z that is explanatory enough for the downstream target network to predict the target attribute. However, if the representation Z contains some information about the semantic attribute S, then the prediction Y hat will have a bias with respect to S. Also, we can ask why prediction tasks do not generalize well. Similar to the previous situation, if the representation Z contains some information about the data domain, the predictor performance will depend on the domain that the input data come from. So, how can we discard the unwanted information from the data representation? An answer is invariant representation learning that aims to learn a representation Z that is independent of S. As a result, the prediction Y hat is independent of S, regardless of the choice of the target predictor GY. This implies that the data owner can provide the representation Z instead of the input data X to an indifferent predictor GY and ensures that there will be no bias in the downstream target prediction. Let's briefly see what the price of invariant representation learning is. If the dependency between Y and S is negligible and we have sufficient annotated data, then there will be no price on the utility of the target task to learn an invariant representation. However, this setting is not in the scope of this paper. On the other hand, if the dependency between Y and S is not negligible, then learning invariant representation will necessarily degrade the utility of the target task. Therefore, there will be a trade-off. In this paper, we focus on the latter setting, where the main challenge is to characterize the optimal utility invariance trade-off. Most existing works only establish bounds on the utility invariance trade-off, and they do not exactly characterize the optimal trade-off from, which results in a suboptimal trade-off. Motivated by the mentioned shortcoming, the goal of this paper is to characterize a near optimal trade-off and a learning algorithm that can achieve the trade-off. Invariant representation learning aims to learn representation Z that minimizes the loss of the downstream target task, while at the same time keeping the dependency of Z to the semantic attribute as small as possible. Depth Z, S is a non-negative measure where it is 0 if and only if Z is independent of S. Lambda controls the trade-off between utility and invariance. If lambda is equal to 0, then this setting boils down to a standard representation learning where invariance is ignored. And when lambda approaches 1, the goal would be to learn a total invariant representation with whatever sacrifice necessary on the target utility. To motivate the idea behind a universal dependence measure that is able to capture all types of dependency between Z and S, consider a simple example where S is a zero mean unit variance Gaussian random variable, and Z is equal to the cosine of pi over 6S. Even though Z and S are dependent together, the Pearson correlation, aka correlation coefficient between Z and S, is 0. On the other hand, the Pearson correlation between Z and the cosine of pi over 6S is equal to 1. This implies that Z is independent of S if and only if the covariance between alpha Z and beta S is 0 for all possible Borel functions alpha and beta. In order to characterize the linear dependency between two random vectors Z and S, it's sufficient to study the covariance matrix approximated by the IID samples contained in the columns of matrices Z and S. All modes of dependence between Z and S in a high dimension turn to be linear. Therefore, the covariance matrix induced by the kernel matrices Kz and Ks can characterize all modes of dependence. More rigorously, consider the functional defined by the covariance between alpha Z and beta S, where Hc and Hs are universal reproducing kernel Hilbert spaces. Notice the linearity of covariance with respect to the transformations alpha and beta. This linearity enables us to uniquely define a linear operator sigma Sc that can generate the covariance between all transformations of Z and S. As a result, Z is independent of S if and only if the covariance operator sigma Sc is 0, or equivalently, its norm is 0. One choice is to use the Hilbert-Schmidt norm of the covariance operator as a universal dependence measure denoted by Hilbert-Schmidt independent criterion. HSIC enjoys a simple empirical estimation using the trace of kernel matrices of Z and S. Given this background information, let's talk about our problem setting. We model the encoder by R functions in the reproducing kernel Hilbert space Hx, where R is the embedding dimensionality. Invoking the representers theorem for kernel methods, we can observe that each dimension of Z is a low-dimensional projection of high-dimensional data if the number of data samples n is large. Similarly, beta S is also a low-dimensional projection of high-dimensional data. This indicates that the joint random variable Z, beta of S is approximately a normal random vector, as has been shown by Hall. Therefore, it's not necessary to transform Z. This motivated us to define our dependence measure by a slight modification at HSIC, which lent itself to analytical tractability in the following. Moreover, we replace the target predictor via the defined dependency between Z and Y as a surrogate to the target loss. The linear version of this dependency has been used previously by supervised PCA and has been shown learning an effective representation for different downstream target tasks like regression, classification, and clustering. We further support the idea of using the defined dependency as a surrogate for the target loss by showing that the representation learned by maximizing the depth of Z, Y can lend itself to a linear regressor that is as optimal as the base prediction of Y given X. In order to avoid learning representation with redundant information where different dimensions of Z are highly correlated to each other, we enforce the encoder F to learn a disentangled representation. This kind of disentanglement is used in PCA. Here, gamma is a regularization parameter to circumvent the nullity of the covariance matrix of Z. Nevertheless, this disentanglement is an invertible transformation, and one can always invert it to get access to original representation. No or invariant representation learning formulation boils down to maximizing the dependency between Z and Y, while keeping the dependency between Z and S as small as possible, controlled by the trade-off parameter lambda. Fortunately, we could find a closed-form solution for the population formulation in terms of generalized eigenvalue problem involving the covariance operators sigma yx, sigma sx, and sigma xx. In practice, we often do not know the distribution of the data to calculate the population solution. Using a uniform empirical estimation for covariance, we were able to estimate the solution empirically. The closed-form solution to this empirical problem is determined by a generalized eigenvalue problem where the covariance operators are replaced by kernel matrices ky, ks, and kx. The naive implementation of our solution is of order of n-cubed computation and n-squared memory usage, where n is the number of training samples. However, using random Fourier feature introduced by Rahimi, abbreviated by IRepL, the computational complexity reduces to order of d cubed, where d is the IRepL dimensionality that is much smaller than n in practice. The memory complexity also reduces to the order of nd, which is linear in n. Finally, with high probability or empirical estimation converge to the population counterpart if the number of data samples n is sufficiently large. As a corollary of our solution, we can characterize the optimal embedding dimensionality R, which is determined by the number of positive eigenvalues in the generalized eigenvalue problem of our invariant representation learning formulation. As the trade-off parameter lambda increases, the optimal embedding dimensionality reduces to enforce more invariance. Now, let's check out some numerical experiments where we compare our invariant representation learning approach denoted by KT-opt to some baseline methods. All of our experiments are on learning fair representation in the sense of demographic parity. To have an intuitive understanding of demographic parity, consider a simple case where both y and s are binary random variables, where y takes 0 or 1 and s can be a red or blue star. The prediction y hat is fair in the sense of demographic parity if the probability of predicting y equal to 1 for s being red is equal to the probability of predicting y equal to 1 for s being blue. In this figure, the probability of predicting y equal to 1 for s being red is 1/2, which is equal to the probability of predicting y equal to 1 for s being blue. Demographic parity violation, abbreviated by DBV, is defined as the absolute difference between these two probabilities. For example, for the right-hand side figure, the difference between these two probabilities is 6/8. In a generalized case, where y and s can be any random vectors, DPV is defined as the average deviation of predicting y among different values of s. So exact invariance is equivalent to DPV being 0. In the first experiment, we considered the fair prediction of employment on New York 2018 census data, where age is the sensitive attribute. The dependency between y and s is 0.40 measured by kernelized canonical correlation, which is a nonlinear generalization of Pearson correlation via kernelization. This large dependency between y and s results in a trade-off between utility and invariance. Since the target attribute is a 4-categorical random variable, the optimal embedding dimensionality is always less than or equal to 3, which is consistent with the observation made by linear discriminant analysis. This figure plots the optimal embedding dimensionality versus the trade-off parameter lambda. As lambda increases, the optimal embedding dimensionality decreases. We experiment with 4 invariant representation learning methods, or KT-opt, the baseline SARL, which is similar to our KT-opt approach, except that a linear dependence measure is used instead, the baseline ARL, and the baseline HSIC. ARL baseline deploys neural networks for encoder, target predictor, and proxy adversary, where SGDA is the optimization scheme. SGDA is unstable and cannot guarantee convergence to a fixed point. The baseline HSIC deploys neural networks to model the encoder and target predictor, and the dependency between Z and S is measured by HSIC. Since HSIC is a non-parametric measure, a simple SGD can train the encoder and network parameters. The first figure plots the target accuracy versus the invariance matrix DPV. We can observe that ARL is very unstable. SARL can only span a small region of the trade-off round due to its limitation of capturing nonlinear dependency. Even though HSIC is stable, however, it's not optimal for some DPV values, which is the result of the suboptimality of SGD in attaining a global optima. Or KT-opt approach, on the other hand, is very stable and can span a large portion of the trade-off round while outperforming other methods. The reason that KT-opt cannot span the entire trade-off round is due to using a single objective scalarized formalization rather than the bi-objective one. The second figure plots the invariance matrix DPV versus or defined depth of Z, S. This result demonstrates that our dependence measure enjoys a non-decreasing relation with DPV, and zero dependence ensures exact invariance. The last figure plots the depth of Z, Y versus the depth of Z, S. Recall that our KT-opt approach actually optimizes the trade-off between these two dependence measures, and there should exist a non-decreasing relation between them, as we can observe it. In the second experiment, we consider the fair prediction of high cheekbone on CelebA dataset, where the concatenation of gender and age is the sensitive attribute. In this setting, the dependency between Y and S is 0.10, which is not negligible. The first figure plots the target accuracy versus the invariance matrix DPV. We can observe that SARL performs as optimally as our KT-opt, since we are using one-hot encoding for both Y and S, and a linear kernel performs as optimally as the universal kernel for one-hot encoded random variables. ARL can only span a small portion of the trade-off round, which is due to the drawbacks of SGD optimization. HSIC can almost span the entire trade-off round. However, it is dominated by our KT-opt for most of DPV values. The second figure plots the invariance metric versus our depth and demonstrate that our dependence measure enjoys a monotonic relation versus DPV, and zero depth ensures exact invariance. This last figure plots the depth of Z, Y versus the depth of Z, S. In the last experiment, we examined the effect of removing the sensitive attribute from the input data in 2018 Washington Census data, which is a very similar data set to the New York data set, except that the target attribute is a binary random variable. The first figure shows the utility invariance trade-off resulting from all methods when the age information is present in the data. The second figure plots the utility invariance trade-off while age information is removed from the input data. The last figure compares removing and keeping the age information for our KT-opt approach. There is almost the same terrain in both keeping and removing the age attribute from the input data for all methods. However, removing the age information from input data slightly degrades the utility invariance trade-off due to the lesser information contained in the input data. To summarize our presentation, two questions are outstanding in invariant representation learning. One, what is the exact trade-off between utility and invariance? And second, what are the encoders that achieve the optimal trade-off, and how can we estimate them from training data? We exactly characterized a near-optimal approximation of optimal trade-off via encoders in reproducing kernel Hilbert spaces. We determined the optimal dimensionality of the data representation necessary to achieve a desired trade-off point. We developed the scalable representation learning algorithms to attain the near optimal trade-off. Thank you for your listening.